As I'm sure you all feel, the idea of going ahead and computing a limit every time we need to find a derivative gets very tedious very quickly. Fortunately, there are some things that we have formulas for and can very quickly find the derivative for them just because there's something that comes up all the time. So let's say we wanted to look at some function that was equal to some constant c. For example, f of x equals 3. We want to know what its derivative would be. So graphically speaking, this is going to go ahead and look like this function. So say we've got our axes here. Here the function is just a constant value. No matter what we pick for x, the value here for f of x is always going to be whatever this constant is. So as you'd imagine, the tangent line is going to just be a flat horizontal line. And so here, because of that, the slope of that line is going to be 0. So here we say that f prime of x equals 0. And it turns out we can just kind of view this as being the slope of the tangent line. Because it's just a horizontal line, it's got a slope of 0. There's no rise over however long we want the run to be. All right, let's look at if we just had f of x. If we wanted to go ahead and find the derivative of this, remember graphically what we're doing is we're just looking at something where as x goes up, f of x is just going to be that exact same value. And so for every 1 we increase in the x, we increase 1 with the y. And because this is just a straight line here, the derivative is going to be 1. So it's just the tangent line of this, which is always going to have that slope of 1. So remember, if we look at the slope of the line y equals x, just 1. We also could go ahead and look at f of x squared. So here, this is going to be the first one where we have to think a little bit harder about what might be going on, and it might be something where we need to go ahead and use that limit definition to compute. So graphically speaking, it looks kind of like this. And so if we're trying to go ahead and find that tangent line and find its slope, we want the limit as h approaches 0 of x plus h squared minus x squared over h. And so foiling that out, we get the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. And so there we can go ahead and get the x squared and the negative x squared to cancel out with each other. And we'll get the limit as h approaches 0. I'm going to factor out an h out of both of these. H times 2x plus h over h. Then these two h's cancel, and then when we plug in our limit, we just get 2x plus 0, or just 2x. So that makes sense. So as we get further and further out with our x values, these slopes are going to go ahead and get larger and larger. And those slopes are going to increase based on what's going on with x. All right, we'll do one more example before we kind of get into a little bit of a rhythm. So here, if we wanted to look at the graph of x cubed, again, this is something where, graphically speaking, it might not be inherently obvious what the slope's going to be. But if we look, when we go from left to right, our value for x cubed is always going up. It's always increasing. And so when we get our eventual formula for it, we'd expect something where no matter what we plug in for x, we should be able to get a positive slope, or at the very least, a non-negative slope. And so it turns out that f prime of x for x squared, or x cubed, is 3x squared. All right, so this leads us then to talking about our formulas for differentiation. It's just some rules we're going to have for us. We've seen some of them, but others are going to be very useful for us to look at. So if we're taking the derivative of a constant, the derivative is going to be 0. If we have the power rule, so if we have x raised to some power, its derivative, if it's raised to the n power, is going to be n times x to the power of n minus 1. So here n is any number. A bit of a special case of this, though, is if we look at the derivative of x to the first power, this will be 1 times x to the 0. And anything raised to the 0 power is just 1, so it's just 1 times 1, which is 1. So all you have to do to find the derivative is bring the exponent down as a thing you're multiplying by and subtract 1 from what you have in the exponent. The sum and difference rule says that if we wanted to go ahead and take two different functions and add or subtract them and take their derivatives, then all we're doing is we're finding the derivative of each function individually and then adding or subtracting accordingly whatever we get for that. So that's just f prime of x plus or minus g prime of x. Now, if we have some sort of constant being multiplied by a function and we're taking the derivative of this, this is the same as taking the constant and pulling it out and then taking the derivative of that function. So it's just k times f prime of x. So say we wanted to go ahead and look at the derivative of this function. So it's 2x squared minus 5x plus 1 plus 3 over x plus the 4th root of x minus x to the pi. Well, the first thing we're going to do is rewrite this. So here, this is going to be 3 times x to the negative 1, and this is going to be x to the power of 1/4. So if we want to go ahead and use this power rule here, we need those to have exponents. So then what we're going to do is we're going to take the derivative of each of these, and we're going to kind of keep these rules in mind. So if we want f prime of x, what we'll do is we'll take the derivative of 2x squared. So notice that if we're trying to take the derivative of 2x squared, it'll be 2 times the derivative of x squared. So it'll be 2 times. In order to find the derivative for x squared, what we'll do is, since it is a power rule, it's just x to some power, we will take the 2, we'll multiply it in front, and then we'll raise x to the power of 2 minus 1, which will just be 1, but for sake of illustrating everything, I wanted to write it out. And then we'll take the derivative of negative 5x, so it'll be minus 5 times the derivative of x, which we said was 1, plus the derivative of 1. So 1 is a constant. So since 1 is a constant, its derivative is 0. Plus the derivative of 3x to the minus 1. So again, because this is something where we're multiplying by this constant 3, we'll pull the 3 out front, and then we will take the derivative of x to the negative 1 using the power rule. Now again, because we're using the power rule, we're going to take this negative 1 and bring it out as a multiple, or a constant to multiply by, and then we'll raise x to the negative 1 minus 1 power, which will be negative 2. We then have plus x to the 1/4, so again, this will be plus 1/4 x to the 1/4 minus 1, and then we'll subtract, since this is x to the pi will become the coefficient, and then it'll be x to the power of pi minus 1. So now we just have to go ahead and multiply through and make our exponents look a little bit nicer. So this is then going to say that f prime of x is 4x minus 5 This is a 0, so it goes away. Minus 3x to the negative 2 plus 1/4 x to the negative 3/4. So 1/4 minus 1 is negative 3/4. And then minus pi times x to the pi minus 1. So not exactly a glamorous derivative, didn't have a bunch of things simplify, but it did kind of allow us to see for a number of different functions using the power rule, constant multiply rule, and then also because we're adding all of these, subtracting them, the sum difference rule, kind of see how we can use that for a bigger function. All right, let's look at another example. So say that the equation of motion for some particle is this s of t. So it's 2t cubed minus 5t squared plus 3t plus 4. So s is going to be measured in centimeters and t is going to be measured in seconds. What we want to do is we want to find the acceleration as a function of time. So remember, acceleration is going to be the second derivative. So if this is our position, so s of t is position. If we want the acceleration, we want the velocity first, so the derivative of s of t. And then after that, we want the acceleration, which is the derivative of velocity, which is the second derivative of the position. All right, so say we want to go ahead and find this acceleration. What we'll do is we'll start by taking and finding s prime of t, which is, of course, our v of t. So that's the thing we're trying to find. And so again, we'll just take the derivative of each individual component and use it to create our first derivative. So if we have 2 times 3t squared for this first one, so we pull out the 2, bring down the exponent of the 3, and then subtract 1 from the 3, so it's t squared, minus 5 times 2t, just to the first power, so since it's to the first power, we don't need to mess with it. And then the derivative of 3t will just be 3, and then the derivative of 4, since it's constant, will be 0. So in other words, this will be 6t squared minus 10t plus 3 for the velocity. So now we want to go ahead and find the acceleration. And the acceleration is just the derivative of the velocity, which is, of course, the second derivative of our position. So that'll be the derivative of this function. So it'll be 6 times 2t minus 10 plus 0, or in other words, it'll be 12t minus 10. This, of course, is our general acceleration function. If we want it after 2 seconds, then we're going to let t, the time, equal 2. And so this will be 12 times 2 minus 10, which is 14 meters per second squared. All right, so let's go through a little bit more of the examples before we go ahead and introduce a few new rules. So a lot of rules today. So these will be kind of the base bone rules that you want to know and memorize, and we'll have some more that you'll want to memorize. Well, let's go through a couple more examples first. Say we want to go ahead and calculate the derivative of some function a, which depends on r, which is equal to pi r squared. So I should say a of r, when r equals 4. So first we want to find a prime of r. And so this will just be the derivative of this. So pi is just a number. So it'll be pi times the derivative of r squared, which will be 2r. So it'll be 2 pi r. Pi r squared, 2 pi r, those look familiar. Anyways, if we want to find the derivative when r equals 4, then all we have to do is plug in 4 for r. So that's 2 pi times 4, or just 8 pi. All right. So we want to find, in this example, points on the curve y equals x to the 4th minus 6x squared plus 4, where the tangent line equals 0, or is horizontal. So tangent line is horizontal. If it's horizontal, what that tells us then is, I think the thing I got to slip, we want to find where the derivative equals 0. So first we need the derivative. So if we want the derivative of this function, this will be a lot of power rule. So if it's 4x to the 4th, it'll be 4x cubed, not squared. Don't know how to write today. Minus 6x squared's derivative, so that'll be 6 times 2x, so minus 12x, plus 4, so plus 0. So we have as our derivative 4x cubed minus 12x. And we want to know where this equals 0. So 4x cubed minus 12x equals 0. Because this is the thing we're trying to do, is set y prime equal to 0. So if we factor, we get x times 4x squared minus 12 equals 0. And we can do a little bit better. We can pull this 4 out as well. So it can be 4x times x squared minus 3 equals 0. And so if you remember, when we're looking at this, either this term has to be equal to 0 or this term has to be equal to 0, or both, in order for this equation to equal 0. So that tells us 4x equals 0, or just x equals 0, will be where one of our tangent lines is horizontal. And then when x squared minus 3 equals 0, which means that x squared would equal 3, which means x would be equal to positive or negative square root of 3. So remember, anytime you take a square root, you have to go ahead and consider both the positive and negative cases. So we specifically asked for the points. So when we ask for the points, we want both the x and the y value. So we want to know then f of 0, f of the square root of 3, and f of the negative square root of 3. So if we plug in 0, that'll be 0 minus 0 plus 4, so that'll be 4. Plug in the square root of 3, that'll be the square root of 3 to the 4th power. So again, if you're not sure how to do these in your head, it can be useful to have a calculator. So you'd want to type the square root of 3 to the 4th power minus 6 times the square root of 3 squared, 2nd power, plus 4. So that gives you negative 5. And you also want to go ahead and know what it is when you have the negative square root of 3. So you have to be very careful where you're putting your negative signs. They have to go in the parentheses because you want to make sure you're raising them to the 4th and 2nd powers respectively as well. And again, we'll get negative 5. So the points where the tangent line is horizontal then are going to be 0, 4, square root of 3, negative 5, and negative square root of 3, negative 5. Okay, so hopefully we've gotten in the swing of some of those more basic rules. What we now want to go ahead and look at are some slightly more complicated rules. So the first of these rules that we're going to get to today is something called the product rule. So the product rule says if you're taking the derivative of two functions being multiplied together, the way you will find it is by taking the first times the derivative of the second plus the derivative of the first times the second. In other words, you'll go ahead and take each derivative, the derivative of each function on its own, multiply it by the other function, and then add those two together. So, say we wanted to go ahead and find the derivative of this function h of x. Now, one thing we could do is we could FOIL it together and then go ahead and take the derivative. But instead, what I want to show you how to do first is the product rule. So, using the product rule, if we wanted to find the derivative of h of x, essentially what we need to do is figure out how we're splitting this up into two functions. So since they are kind of have their own parentheses, we're going to call this first one f of x, and we'll call this second one g of x. So it'll be the first, so it'll be x squared plus 1 times the derivative of the second. And so the derivative of 3x, or x cubed minus 2x, will be 3x squared minus 2, plus the second one, so x cubed minus 2x, times the derivative of the first one, so just 2x. So just to kind of point out what each of these are, this is f, this is f prime, this is g prime, and this is g. And so then we can go ahead and FOIL here, and we'll get 3x to the fourth, multiplying the first two. Multiplying the outer, we'll get minus 2x squared. Multiplying the insides, we'll get plus 3x squared. Multiplying the last ones, we'll get minus 2. And then here we just have to multiply the 2x by both things. So we'll get plus 2x to the fourth minus 4x squared. All right, so if we want to go ahead and combine all of our like terms, we could have stopped here, most likely. But if we want to go ahead and make sure that both sides end up being equal at the end of the day, we've got our x to the fourth terms, our x squared terms, and our constant term. So for the x to the fourth terms, we should get 5x to the fourth. For our x squared terms, we'll get negative 2 plus 3 is a positive 1, minus 3, or minus 4 is a negative 3, so negative 3x squared, and then minus 2. Instead, however, we could have gone ahead and FOILed first. So in that case, h of x will be these two multiplied together, so the first term, so that'll be x to the fifth, and then we'll have the outer term, so this will be minus 2x cubed. Then the inner terms, so this will be plus x cubed. And then the last two terms, so that'll be minus 2x. And so combining all that, we'll get x to the fifth minus x cubed minus 2x. And so this then is the thing we want to go ahead and take the derivative of. And so if we take the derivative of this, derivative of x to the fifth is 5x to the fourth. Derivative of negative x cubed is negative 3x squared. And the derivative of negative 2x is minus 2. And so indeed, both of these match up. So it doesn't matter which method you use, you should be able to get the same answer regardless. In fact, very good practice on a lot of these problems will be seeing if you can find a way to use more than one type of rule and make sure you get the same thing. And if you don't, then maybe you've made a mistake in one or more places. So that was our first extra rule. The next extra rule we want to look at is something called the quotient rule. And so here we have one function being divided by another, and we want to go ahead and find its derivative. So there's a kind of nice mnemonic to help remember this. So this is considered the low function, and this is considered the high function. And so how it works is that you want the low function times the derivative of the high function minus the high function times the derivative of the low function divided by the low function squared. And so writing it again without all the x's, it's g times f prime minus f times g prime all over g squared. So how it's typically referred to is low d high, and this d of course is for derivative, minus high d low all over low squared. So when you're looking at the quotient rule, if you can remember which one's your numerator and denominator and what means high and what means low, if you remember low d high minus high d low all over low squared, that'll be a way to remember the quotient rule a little more easily. Alright, so let's say we wanted to go ahead and find the derivative of x squared plus 3x over x to the fifth plus 7. So it's not something where we can very easily figure out what we should be doing to kind of divide or factor or some way to reduce this in any way to make it something we can take the derivative normally. So we want to go ahead and have our high function, so our f of x, and our low function g of x. So if we want to go ahead and find the derivative is going to be the bottom function, so that'll be x to the fifth plus 7 times the derivative of the high function, so low d high, derivative of the high function, if this is x squared plus 3x, it'll be 2x plus 3 minus the top function, x squared plus 3x, times the derivative of the low function. So if it's x to the fifth plus 7, we'll have 5x to the fourth as our derivative, because again, the 7 part, the derivative of that will be 0. And that'll be all divided by the denominator of x to the fifth plus 7 squared. So again, just to kind of spell some things out, this is f prime, this is f, this is g prime, this is g, and all of this is g squared. Alright, so our next question is going to ask about a hyperbola. So we want to know at what points on the hyperbola x times y equals 12 is the tangent line parallel to the line 3x plus y equals 0. So you might be thinking to yourself, well, none of these are really in the the slope-intercept form that we're used to. And so we want to first go ahead and solve both of these for y. So if we're given something like this, we'll go ahead and rewrite it as y equals 12 over x, or 12x to the negative 1. And if we have something like this, if we solve for y, we'll have y equals negative 3x by subtracting over the 3x. And so we want to go ahead and figure out where the tangent line of this equation has a slope parallel to this one. So in other words, we want to figure out where the derivative of this function equals negative 3. So this is the slope. So let's rewrite the question. What values of x are there such that the derivative of 12x to the negative 1 equals negative 3? Alright, so first we want to go ahead and find the derivative of this. So if this is our y, we'll call it f of x for now. If we want to find f prime of x, that will be negative 12x to the negative second, or negative 12 over x squared. And so what we're saying is we want to take negative 12 over x squared and set it equal to negative 3. And solve for x. So if we do this, first we'll go ahead and get the x squared out of the denominator, so we should get negative 12 equals negative 3 times x squared. Then we'll divide both sides by negative 3, so we'll get that 4 should equal x squared. And then when we take the square root, we have to remember that we have to consider both positive and negative numbers that could get us there. So x will equal 2, or x will equal negative 2. So these are our different values of x that will get us there. If we want to know what points we're looking for, we just need to find f of 2 and f of negative 2 for this function f of x. And so if we plug in 2, we'll get 12 divided by 2, which will be 6. And if we plug in negative 2, we'll get 12 divided by negative 2, which is negative 6. So our points are going to go ahead and be the points 2, 6, and negative 2, 6. So again, in some cases, all we care about are the x values. In other cases, we are looking for specific points on a line in order to be able to figure out exactly what we're looking for. All right, so let's say I gave you this table here that told you some things about a function and its derivatives. What I want you to do is take a minute and see if you can find out, based on this, the answer to all of these questions. All right, I assume you got it. Cool. So, if we want to look at f times g prime of 1, this is saying that we need to use our product rule. So we want f times the derivative of g plus f prime times g. And if it's of 1, that'll help us narrow down what function value we have. So this will be f of 1 times g prime of 1 plus f prime of 1 times g of 1. And so f of 1 is 4, so this will be 4 times g prime of 1, which is 2, plus f prime of 1, which is negative 3, times g of 1, which is 7. So this will be 8 minus 21, which will be negative 13. Okay, now let's say we wanted to go ahead and find f over g prime of 1. So again, this will require us to then use our quotient rule to use this. So this was product rule. This is quotient rule. And so remember, our quotient rule is low d high minus high d low all over low squared. So if we want low of 1, that'll be 7, times the derivative of the high, which is negative 3, minus high, which is 4, d low, which is 2, all over low, which is 7 squared. So that is negative 21 minus 8 over 49, or negative 29 over 49. Alright, so now let's say we had f of x was 1/2 x squared times little f of x. Well, this is going to take this 1/2 x squared and multiply it by our f of x, so this will actually be a product rule. So here it'll be important to recognize that we have two functions. This will be one of them, and of course f of x will be the other one. So we'll go ahead and we'll find the first. So this will be the first is 1/2 x squared times the derivative of the second, so little f prime of x, plus the second times the derivative of the first. So if it's 1/2 x squared, multiply the 1/2 by the 2, and we'll just be left with x. So if we wanted f prime of 1, that'll be 1/2 times 1 squared times f prime of 1, which is negative 3, plus f of 1, which is 4, times x, which is 1. So that'll be negative 3/2 plus 4, which will be 2.5 or 5/2. And then last one, which probably should have been the hardest, is this doozy. So if we have x over f of x times g of x, we want to know what h prime of 1 is. So if we treat this as our high function, we treat the whole bottom part as our low function, we want to go ahead and start with quotient rule here. And so remember that when we're trying to do the quotient rule, so find h prime of x, it is low d high minus high d low all over low squared. So of course low is f of x times g of x. So when we're looking to do this low d high, we're starting with f of x times g of x times the derivative of the top, which in this case is just 1. So times 1 minus the high part, so x, times the derivative of the bottom part. Now if we're multiplying f and g, this is actually going to go ahead and be product rule. So quotient rule, then product rule. So you get to use both. Isn't that exciting? So this will be f g prime plus g f prime. I note that at this point I've started not using the x's. So again, these are functions with respect to x, so you could put that parentheses x in there. However, sometimes you'll confuse yourself when you're trying to write not only the function but also the variable, and it'll be kind of tricky to see where things are. So I'm going to stop putting the of x part for the moment, and this will be all over f of x times g of x squared. And again, I'm not going to put the x part for a second. So that means if we want h prime of 1, we'll go ahead and plug in the 1 into the things we need to. So f of 1, we said from before, and so you might want to reference this part at the top of the page. It'll be kind of out of the view for a second. F of 1 is 4, so this will be 4 times g of 1, which is 7. So 4 times 7 times 1 minus x. Now we just said x is 1, so that'll be 1 times, and then in parentheses here, f, which is 4, times g prime, which is 2, plus g, which is 7, times f prime, which is -3, all over f times g, so that's 4 times 7 squared. Well, that's a lot. So what we should get is 4 times 7 times 1 is 28. 4 times 2 is 8. Minus 21 is -13, so minus -13 all over 4 times 7, which is 28 squared, which is 784. So this will be 28 plus 13 over 784. So we'll get as a final answer 41 over 784. So again, first thing we had to do was figure out, based on our rules, what the pattern should look like. From there, we then plugged in our value of 1, so that way we could try to find what it is we were looking for. All right, we're almost done. We've got one more page. Okay, so let's say we wanted to go ahead and differentiate this function here. Since we're talking about our function being in terms of t, we don't know what a and b are. They're just going to be numbers. So a and b are numbers. T is the variable. Okay, so in this case, we're taking our derivative now with respect to this variable t. So before we've been using x a lot, but we don't always have to use x. It's really just a placeholder for whatever we decide to use. So say we wanted to use t instead. If we wanted to go ahead and find the derivative of this, we could do one of two things. We could use the product rule, or we could distribute this through. So let's use the product rule because it's good practice. And so in doing the product rule, we will get, this can be our first function, and this can be our second function. So then our f of t will be the first times the derivative of the second. So a is just a constant, so it's 0. And b times t will just give us b, so 0 plus b, plus the second, a plus bt, times the derivative of the first. So remember that the square root of t is the same as t to the 1/2. So this will be 1/2 times t to the -1/2. And so again, we just take the 1/2, we multiply it down in front, and we subtract 1 from the exponent. So 1/2 minus 1 will be -1/2. And so this will give us then b times the square root of t plus 1/2 times t to the negative 1/2 times a plus bt. So is it the prettiest thing ever? Not really. They're not all going to come out pretty though. And when you're doing your homework on WebAssign or wherever, sometimes it's just good enough to leave it at a simplified form like this, and so that's what we're going to do here. All right. One last example. Say we wanted to find the equation of the tangent line to this curve, y equals the square root of x over 1 plus x squared at the point 1, 1/2. So again, to find the equation of the tangent line, since we want to get it as y equals mx plus b, we just need our point, which is 1, 1/2, and we need our slope, which will come from y prime of 1. So here, which rule should we use? That's great, class. Glad you figured it out. It's the quotient rule. So, remember we're just doing low d high minus high d low all over low squared. So if we want to find y prime, that will be the low, which is 1 plus x squared, times the derivative of the high. So the derivative of the square root of x is 1/2 x to the negative 1/2 minus the high, so square root of x, times the derivative of low, which is just 2x, all over the bottom squared, so 1 plus x squared squared. Now note that we're not actually interested in having a solid formula for this derivative. So there's a lot of simplifying we could do, but it's not necessary for us. So what we are interested in is going ahead and plugging in 1. So we want y prime of 1. And so this will be 1 plus 1 squared times 1/2 times 1 to the negative 1/2 minus the square root of 1 times 2 times 1 all over 1 plus 1 squared squared. That's a lot of 1's. So 1 plus 1 is 2. So we get 2 times 1/2 times 1 to the negative 1/2. So 1 to any power is going to be 1. So this is 2 times 1/2 minus the square root of 1 is 1. 2 times 1 is 2. And 1 times 2 is 2. All over 1 plus 1 squared. 1 squared is 1. 1 plus 1 is 2. 2 squared is 4. So this will be 1 minus 2 over 4, or negative 1/4. And so then the equation of the tangent line, if we want to find that, is going to require us to go ahead and use our slope and our point. So we want y equals mx plus b. We just found the m. We know our point for y and x, so that means that 1/2 equals negative 1/4 times 1 plus b. So that means that we have 1/2 equals negative 1/4 plus b. If we add the 4th over to the other side, that means b equals 3/4. And so the equation would be y equals negative 1/4 x plus 3/4. Alright, so you'll want to get very comfortable using these rules to quickly take derivatives without having to know how to do the limit definition. Because I promise if you start looking at the limit definition for these, you're gonna be in for a long haul.